It's like the wild things yesterday. Oh, it's hungry, so I was like, okay. You literally that like the red was stuck in the back where whatever. I ordered the roof of my mouth. It still hurts. Why would you not test it? I did. I think it was like the first bite was way too hot. And then like tried to finger on it. And you put your finger on it and it burns. No, but it wasn't like that. No. You burned the roof of your mouth. Yeah. So it wasn't that hot. No, it was very hot. I didn't. I had the first bite and the other ones didn't seem so bad. I think they might have been just like that's yeah. Stand up rails. And I'm pretty close. I thought. You know, going to work, just like real estate, it's just a lot. Like 6. What? The 70s. Well, like 90s. Actually, I know. I'm kidding. I'm just slandering. When he's in AW, honestly, it was kind of big. The money targets. Oh yeah, Derek is good. Derek's actually I had the problems. You know what? They do funky stuff. They do funky stuff and funk basic. It's like not special. We got the square burgers. Hey, we got AWs with the flavorful bug burgers. Hey, I have a friend that best root beer. That's okay. That's the perfect flow to the bars. Oh, bars is like this. You're so quick. But AW's the best root beer. That's why I guess 20. It's the bars. That's probably yeah. Well, just kind of like shells and all that stuff, but it's not fast turning. But like it's
Can I give this to you now?
Yep.
Perfect. Thank you.
Good.
Why aren't you tracing the you have.
Did the two of you get your circuit working?
Yes, we can.
Oh, nice.
Yes.
Yeah, sweet.
Definitely.
Yeah, sweet.
It always comes down to a wire that's connected or
Oh,
something
yeah,
so silly.
Yeah, sweet. Good.
Yeah, we got there. It was very exciting.
Yes.
You get stabbed, you're gonna just want to move it out. You got your little window location.
I also know a lot about it's like
All right. I've got some bad news for you. Today is the last Phys 231 class. Yes. All right, so a couple of reminders before we get started. One is that we are going to collect your lab notebooks at the end of your lab session. And so if you're in the morning session, 11:50 is the due time. If you're in the afternoon, it would be 3:50. Just to let you know, if you are in the afternoon session, I will have to leave at 3:50 in order to get to a class of one of my kids. But if you want extra time, as I said last class, if you're in the afternoon section, you can come and join part of the morning section if there's room available, and I think there will be. Likewise, if you're in the morning session and you need extra time, you could feel free to come to the afternoon session when you have that time. The expectations for what should be in your notebook when you submit it is on the course website. So there's a November 22nd entry and you can read it there. Final exam, they've scheduled that for December 12th. So I guess that's a week from tomorrow, I think. And unfortunately, it's in evening time, but there it is. There are practice finals and solutions on the course website. If you go to the October 7th entry, we no longer cover all of the same material that we covered for those past exams. So in this October 7th entry, it tells you which questions you can skip because we will not be asking you about topics we didn't cover. For the final exam, you can bring a formula sheet that you create yourself, just a standard letter size piece of paper. You can put whatever you want on it, both sides. If you want to type something out in some micro font and print it, I don't care. Like, have at it. It's up to you. It's your piece of paper. Do whatever you like. And then calculator, you can bring a calculator. Anything that can't go online or communicate with other devices is fine. So graphing calculators are fine. Things like cell phones are not fine. Okay. Any questions about any of that stuff?
The cheat sheet is double-sided.
Yeah. Yeah. So yeah, both sides. I'll put the similar information on the course website as well. Yeah.
I thought we could do any, but that, I'm assuming that means it's up to us to provide our own equations, standard units, and everything else. I don't think there is much for this course.
Yeah, I'm not giving you a formula sheet, so you make your own. You do whatever you like. It's wide open. You can write solutions to example problems. You can write formulas. You can draw happy faces, whatever you like. Yeah. Did you? No. Yeah. All right. Anything else? Yeah.
To be the same next week.
Yeah, I'll be around. So if you want to see me outside office hours, then you could just send me an email and we'll figure out a time. Yeah. All right. Okay. So what I want to do today is I want to finish up by doing an application of these logic gates that we designed and built. So these are things like AND gates and NAND gates and OR and NOR and XOR and XNOR and all that stuff. And so the application I want to look at is adding up binary numbers. And so what we're going to try to do is we're going to try to ultimately design a fairly complex circuit. I think in the end, we'll find out, but I think in the end, we're going to design a 66 transistor circuit today to add up binary numbers. But we will do it by having various levels of abstraction. Okay, and so let's see how this is going to work. So suppose we want to start simple and we want to add together just a pair of bits. One bit could be a 0 or a 1. And so one possibility of adding 2 bits is 0 plus 0. And that's just going to be 0. We could do a 0 plus 1, and that would be a 1. We could do a 1 plus 0, which is also 1. Or finally, the last possibility, if we're just adding 2 bits, is to add 1 plus 1, which of course, in our decimal system is 2, but in the binary system would be 1, 0. So this would be like 2 to the power 1 times 1, which is our 2 plus 0 times 2 to the power 0. So, which is 0. All right. So what we can see immediately from this is that our device that we're going to use to add these bits will have to have 2 inputs, obviously, but it also have to have 2 outputs because we need to be able to represent the binary 1, 0. So what we could imagine is that these other ones, the outputs will actually be 0, 0, 0, 1, 0, 1, or 1, 0. So our bit adder will require 2 inputs and 2 outputs. Okay, and it's going to turn out that this is not actually going to be that difficult to design. What I'm going to do is I'm going to construct something like a truth table for our bit adder. And all I'm going to do is I'm just going to list these possible inputs and the corresponding outputs from what we've already drawn above, right? The inputs are always going to be the same possibilities. So there they are. And the outputs, what I'm going to do is I'm going to separate the outputs and I'm going to make a clear distinction between the 2 columns. In the column on the right, I'm going to put 0, 1, 1, 0. And then on the column on the left, I'll put the 0, 0, 0, 1. Okay. So if you look at this truth table, let's just focus on the column that's on the left-hand side here. For these inputs and this output, what kind of operation does that look like to you? It's an AND gate, right? I get a high only if A and B are high. So this one is the AND operation. What about the one on the right? Yeah, it's an XOR, right? So it is A or B excluding high case. So the high case is 0. So this is exactly the XOR operation. And so that means it's pretty clear how we should build our bit adder. So let's consider the following circuit. All right, so I'm going to draw our inputs A and B. And then we'll first feed an XOR gate. And so remember the circuit symbol for the XOR gate looks something like this. And I'm going to call this output S. And S stands for sum. All right. And then we need a second output. And that second output is going to come from an AND gate. So we'll draw the AND gates. And I'm going to call the output of that AND gate C. And that's going to stand for carry. And so we need to make this last connection here. And there we go. And so this circuit would construct this exact truth table above. the sum column is here, so we'll say that this column is the S output and the other column is the carry output. And the carry is because if we have a 1 plus 1, I have to carry over to the next higher, the next least significant bit. So if this is the least significant, this would be the next least significant. All right. So this entire circuit is usually represented as a single block. And so that's what I mean by different levels of abstraction. We've already done some abstraction here. The AND gate, we know how to make out of 2 transistors, right? And so this is already an abstraction of a 2 transistor circuit. Yeah.
Isn't it also a carry, because when you make your ALU, it'll carry that input to the next ALU?
So I don't know what an AOU is. Okay, yeah, I'm gonna call this circuit a half adder, and then we're gonna design something that's gonna combine half adders, and that's probably what you're getting at, I think. Now, we'll see that in a second. So this is 2 transistors. And then this XOR, if you've looked at the assignment 6, which is one we didn't collect and grade, the first question in assignment 6 is to make an XOR gate out of NAND gates. And so this XOR gate, it can be constructed from 4 NAND gates. And each of those NAND gates is 2 transistors. And so this is 8 transistors. All right. So this circuit is called the half adder. I don't know, you're all too young, but whenever I hear half adder, it makes me think of Blackadder, if anybody knows that comedy. It's a British comedy, it's pretty funny. It's Mr. Bean is the guy who's in it, but he's not the Mr. Bean character. All right, anyways, we're gonna represent this circuit as a half adder, and we'll just call that HA. All right, and so this circuit has a total of 10 transistors. All right, so that's fine. Adding 2 bits together is interesting, I guess, but it's not that useful, right? It's pretty limited in what it can do. So the next question is, how can we add sequences of longer bits? Okay, so for example, what I might want to do is add up these 2 4-bit numbers. And so what I would do is I'd say 1 plus 1. Well, that's going to be a 2. So I'm going to get a 0 and I have to carry 1. And I get 1 plus 0 plus 1. I get a 2 again. So 0, carry the 1. 1 plus 0 plus 1. I get 2 again. So I get a 0, carry the 1. And I get a 1 plus 1 plus 1, which is 3. And then the binary representation of 3 is going to be 1, 1. Okay, and so that's the sum of these 2. And so I want to be able to do this kind of operation using just logic gates. All right, so to add a longer string or sequence of bits, we require an additional input. Right, so now I'm not only adding together, when I do this operation 0 plus 1, I'm not just adding two things. I actually have to allow for the possibility that there was a carry forward from a previous operation. So we're going to need a third input. So we need an additional input to handle the possibility of a carry forward from a previous operation. Okay, so I'm gonna draw this, I think, on the next page just to make the space. So what we're gonna do is we're gonna take two half adders. And I'm gonna have also an OR gate. So this is an OR. All right, so the first half adder will have our A, B inputs. And then we're gonna take one of the outputs from the first half adder, we'll feed it into the input of the second one. And we'll have the third input, C in, we'll call it, will go into the second input of the second half adder. So this would be the carry from a previous operation. It's going to be a 0 or a 1. Okay, and then our OR gate will look like this. This output will be a C out. This will determine if we have a carry to bring over to the next operation. And then we'll have this output S. So I'm going to label some of these intermediate points. We have each half adder has an output, a carry, and a sum. So for the first one, I'll label them S prime and C prime. For the second one, the carry will be C double prime. And then what we'll do is we'll try to construct a truth table for all of these things. So this entire circuit, I'll put inside of a blue box. This entire circuit will abstract another level of abstraction. And so this is going to be called a full adder. Okay, and so this full adder will represent as FA, and it'll have the inputs A and B and the carry in, and then we'll have a carry out and an S. So let's just see, each of these half adders has 10 transistors. So there's 20 for the two half adders. And then the OR gate, remember we made the OR gate by putting two transistors in parallel. So there's another two transistors. This is a 22 transistor circuit. So this is a 22 transistor circuit. And what's nice about this is that, you know, if you were to actually built this out of transistors, it would be a pretty complicated circuit to construct. But by having these levels of abstraction, you know, you just have these simple blocks that do simple operations, and that's easier to keep track of. So what we'll do is we'll first confirm that the full adder appropriately just sums 2 bits. So that's the first objective. So let's verify that the full adder, correctly sums 2 bits. So there's 2 cases to consider. One case is when we don't have a carry from a previous operation, and that's the one we'll start with. And so we'll make C in is just a low. All right, and so we'll just make some truth tables. And it's gonna be, I guess, a little bit of a big one, but we'll have our inputs A, B, and C in. Then we're gonna have the output of the first half adder, C prime and S prime. So we'll have C prime and S prime. And then we'll have the outputs of the second half adder, which I'll C double prime and S. So we'll have C double prime and S. And then we had the C out, and I'll just repeat S here, and then we'll have our decimal equivalent in this last column. Okay, and let's divide this out into inputs, first half adder, second half adder, final output, and decimal equivalent. So what we're gonna do is we'll list all of the inputs, and we're doing the case where C in is always 0. We'll do the other case as well. All right. So this is just a half adder, right? So it's just adding the A and B, and we've already figured out what that does. If I have 0 plus 0, I just get 0. If I have 0 plus 1, I'm going to get 1, so I don't have to carry everything or anything, and we just get 1 for the sum. Same as 1 plus 0. And then here, 1 plus 1 is 2, so I'm going to have to carry over a 1. And we'll get 0 in the sum because this is 1 times 2 to the power 1, which is just 2. Okay. Let's go back and look at this full adder. The next thing we're going to do is we're going to sum S prime and C in. Okay, we're just going to do that sum. We know what the half adder does. So this is going to be S prime and C in. So what we're going to focus on are adding those two columns right now. So 0 plus 0 is going to be zeros. 0 plus 1 is going to be a 1 in the sum and 0 carry. 0 plus 1 is a 1 in the sum and a 0 in the carry. I think. Am I doing this right? Oh, sorry. Yeah, I am. I'm just in the wrong spot. Okay. And then we have a 0 plus 0, which is zeros again. Okay, good. So far, so good. This S column is just repeated here, so I'm just going to copy that down. And all that's left to do is to check C out. Now, what was C out doing? C out was the OR of C prime and C double prime. I mean, it makes sense, right? If we have a carry from either of the adder operations, we should carry that to the final output. So it's C prime and C double prime, and we're going to do an OR operation. So we want to focus on C prime and C double prime now, and we'll do that OR. So 0 or 0 is a 0. 0 or 0 is a 0. 0 or 0 is a 0. And then we finally have 1 or 0, and that's going to be a 1. And then you could already see that what we have is binary 0, 1, 1, and then this is the binary representation of 2. And so we get 0, 0, so 0, 1, 1, and 2. And that looks to be correct. All right. So let's try the other case. The other case is we're just going to set C in not to be 0, but to be 1. And let's just see if we get the right kind of truth table in that case. So if Cn is equal to 1, this is like adding A plus B plus 1. Okay, and so the circuit we're going to analyze now is we have our full adder, we have our A and B inputs, those can be the usual things. And then this is going to be our Cn, and we'll just put a high here, it'll be 5 volts. And then we want to know what our C out and S. Okay, so we got to make the same table. S prime, C double prime, S, C out, S, and then the decimal equivalent. Okay, Cn is always going to be 1 in this table, and then we have our possibilities for A and B. So, all right, the first half adder just adds the first 2 columns, A plus B. Okay, we can look at that there, right? First half adder is just adding A and B. So it's no different than the first table we did. So we would get 0, and then we'd get a 1, then we get a 1, and then we get 1, 0. Exactly the same. Okay, so the next half adder is going to be S prime and C in. Okay, so we're gonna look at S prime plus C in. This one will be different now because we have 1s here instead of 0s. So we get 1 plus 0 should be a 0, 1. Now we have a 1 plus 1, and so that will be a 2. So we would carry 1 and have a 0 in our sum. 1 plus 1 is a 2 again, same thing. And then 1 plus 0 is going to be a 1. All right, I think that looks all right. So what are we going to do? We're going to copy S down, that's not going to change. And then we have an OR operation. Let's just remind ourselves, what are we taking the OR of? C prime, C double prime. Okay. So C prime or C double prime. Okay, 0 or 0 is a 0. The decimal equivalent is 1. And that makes sense because we have 0 plus 1 is 1. All right, 0 or 1 is now going to be a 1. And so the decimal equivalent of this is carry 1 to the next higher decimal place or digit place. And so this is binary 2. So that makes sense because we have 0 plus 1, which is 2. We should get the same thing for this next one, 0 or 1. And so that's going to be a 1, and this is a 2. And now we have a 1 or 0, we get a 1 again. And now this is the binary representation of 3. And that makes sense because we have 1 plus 1 plus 1 is 3. Okay. So our full adder is working as expected. So what I want to do now is I want to string together full adders so that we can add an arbitrarily long string of bits. So adding arbitrary length bits, lengths of bits. We're going to do that by cascading full adders. Okay, I'm going to try to do an example of adding up strings of 3-bit numbers, 2 3-bit numbers. So we're going to use 3 full adders. Okay. So what we'll do is we'll make this the least significant digit, and then this is the most significant digit. So we'll start from least, maybe I'll label it over here. So this is gonna be least significant bit, and this will be the most significant bit. All right, so each full adder has 3 inputs, and so we have to start with that. When we're adding the least significant bits, there's no previous operation, so we just have to ground this carry. So this would be our Cin input. And then we've got 2 other inputs, and I'm gonna call those A0 and B0. Okay, then what we're gonna have is we're gonna have an output that is gonna be, we'll call it S0. And then we have a carry out. That carry out is gonna feed in to the carry in of the next full adder. So we'll call this C0. Okay, and then we're gonna have some more inputs. We'll call this A1 and A2. We'll have a sum. Sorry, no, I don't. I want this to be B1, and this will be S1. We're gonna have another carry out, and that's gonna feed in to the next full adder. So this will be carry 1. And then we have in here A2 and B2. We have S2. And if we are adding only strings of 3 bits, then there's nowhere to take this carry to the next adder. And so it's just going to be part of our final output. If I add 3-bit numbers, there's a possibility that the output will require 4 bits, and the 4th bit comes from the last of the carry operations. And so this will be our final output. And so what I want to do is I want to just verify that this does work for some example numbers. So this cascade of full adders correctly sums pairs of 3-bit binary numbers. And then we said every full adder is 22 transistors, at least the way we've constructed our logic gates. And so what we really have here is a circuit of 66 transistors. This is a circuit of 66 transistors. Right, and that's fairly complicated, right? If you were to sit down with a bucket of transistors and say, okay, design something to add up bits, that would be a challenging thing to do. But the way we've done it little bits, little parts at a time, and it was successful. So let's test this thing. So let's try an example. Let's try A is going to be equal to 1, 0, 1, and B is it going to be, I'm just making something up here, 1, 1, 1. And what we're going to try to do is we're going to try to evaluate A plus B. And that's going to be equal to 1, 0, 1 plus 1, 1, 1. And let's see, so we would get 1 plus 1. Let's figure out what we're supposed to get. 1 plus 1 is going to be a 2, so it's 0, carry 1. Then we get 1 plus 0 plus 1 is 2, so we get 0, carry the 1. And then we get 1 plus 1 plus 1 is 3. And so it'd be 1, carry the 1. Let's just list out some binary numbers here. Zero, one, 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 almost where I want to be. 1 0 0 1 1 0 1 0 1 0 1 1 1 1 0 0. Okay, so this should be 0 1 2 3 4 5 6 7 8 9 10 11 12. Okay, 1 0 1 is 5. So this is A. And then 1 1 1 is 7. And so here's our B. And then the last one we have is 1 1 0 0. And that's over here. That's 12. And this is A plus B. So that's what we're going to do is we're going to make our inputs these strings of 3 bits. And we're going to look for an output that looks like that. All right. So A is 1 0 1. And B is 1 1 1. And let's see what happens. We have our C in is 0 here. All right, so the full adder is going to add 1 plus 1 plus 0, which is binary 2. So our sum, our output of our sum should be a 0 carry the 1. Okay, and so then we have a 1 here. And then we go 0 plus 1 is again binary 2. So our sum is 0, and then we have to carry the 1 again. And then we have 1 plus 1 is binary 3. This time the sum is 1, and we have to carry forward the other 1. There's nowhere to carry it to except for our output, and our output would be 1 1 0 0, just like we predicted it should be. What's nice about this is, you know, to add any lengths of bits is no different, right? If I had 8-bit digits and I wanted to sum those, I would just have 8 of these full adders. 22 transistors each, a circuit of 8 times 22, whatever that is, 176 maybe. So there's no limit to doing this. Like our digital oscilloscopes have a certain number of bits of resolution, and so it would have to do operations on whatever that number of bits is. And if it was a summing, like we have math mode on our oscilloscope, and so if we wanted to sum 2 voltages from channels A and B, then I would just maybe add up 8-bit numbers and display that as my math output. And I would do that for every single voltage at every time across the screen. All right, good. So that's what I wanted to end with today. I'm happy to, we've got, let's see, we have like maybe 10 minutes, so I'm happy to take any questions if anyone has anything. But other than that, that is a wrap. All right, any questions? Yeah. Oh, I don't know, just the point was just we've designed these logic gates, and I just wanted to show you one application. So the type of thing that you would master is not necessarily coming up with the design of something like this, but rather just analyzing the operations of the gates. That's the part that you would be expected to do on the final exam. Yeah. Anything else? All right. Thanks very much, everyone. Have a good evening, and we'll see you.